How are cholesterol and other molecules like coenzyme Q10 biosynthesized in your cells? The story starts with acetyl-CoA. And of course, the structure of CoA is big and kind of complicated. We don't need to remember it because the function of acetyl-CoA is simply to deliver a C2 unit, an acetate in biosynthesis. Not just this biosynthetic pathway, but others too. Condensation of one acetyl-CoA with a second acetyl-CoA gives a Claisen condensation product, to use an old term, a 1,3-dicarbonyl. I think you can see that if we take third CoA and add it to the ketone, we will get a tertiary alcohol, giving us this di-CoA product. An enzyme cleverly hydrolyzes one side. It creates a chiral center in the middle. That tertiary alcohol is HMG-CoA, 3-hydroxy, 3-methyl butyryl CoA, HMG-CoA. Now comes the key step in the biosynthetic pathway. So we have now one free carboxylic acid, one as an ester with S-CoA, it's a thioester. Then the star of the story enters. Enter stage right, HMG reductase. This is the enzyme inhibited by statins. Statins like atorvastatin, brand name Lipitor, and rosuvastatin, brand name Crestor, two of the most powerful statin-reducing drugs. If the pathway isn't inhibited, then HMG reductase will reduce the carboxylic acid to give a primary alcohol. And that molecule is called mevalonate. This is the mevalonate pathway. I'm sorry, I have to go black box here because many steps are involved. They're hard to remember. I can't remember them. I wouldn't expect anybody to do that. But the salient feature is we stop at the first terpene in the sequence, and that is isopentenyl pyrophosphate, IPP. You can see the C5 fragment that looks as though it comes from isoprene, but of course it doesn't. It's derived from mevalonate. That IPP unit is then assembled in many steps to squalene. If you look closely at the structure of squalene, you will see two C5 units put together head to tail on one side, two C5 units put together head to tail on the other side, and then those two dimers assembled head to head. Let's take squalene and let an enzyme oxidize it to squalene epoxide, specifically on one double bond and not two. Clever enzyme. Protonate that epoxide and draw the molecule in a different conformation. There now follows some of the most beautiful curly arrows in organic chemistry. The protonated epoxide acts like an electron sink. It draws away electrons from a trisubstituted bond, forming a carbocation, which draws electrons from another trisubstituted double bond, forms another carbocation, and then draws electrons from a third trisubstituted bond and forms this time a cation by a 5-membered ring formation, not 6. In that domino sequence, we generate an A, B, C, D ring system. That's good, but it's not a steroid yet. And it's not the final product either. If we look at what's going on in that red box there needs to be a methyl transfer and other things happening before we get a steroid. And that is all taken care of by this one enzyme. Remarkable. The product then of the enzyme catalyzed reaction is lanosterol because it has that double bond between rings B and C. But in a series of many more steps, lanosterol is converted to cholesterol. Cholesterol biosynthesis. So just to remind you of the big picture, if we don't get mevalonate because of inhibition of HMG reductase, then the steps leading to cholesterol will be impeded and then less cholesterol will be made. Unfortunately, cells have a feedback mechanism. If they sense depleted cholesterol, they send back a signal to make more. So this sets up a tension in the cell. Mevalonate is also a biosynthetic precursor for other things, and notably other steroids, including the sex hormones. It's a precursor for vitamin E, and it's a precursor for coenzyme Q10. Coenzyme Q10 is important. A doctor cannot measure coenzyme Q10 levels in tissues like the heart, the brain, muscles, the liver simultaneously. Supplements may work, but they may not. We can't tell from pharmacokinetics where Q10 supplements will go. But we do know where they need to be in the mitochondria because Q10 is involved in the second step of the four-step electron transfer process, which feeds a proton potential to ATP synthetase, this remarkable enzyme that acts like a turbine to generate ATP from ADP and phosphate. Therefore, this process, four electron transfer steps leading to a proton potential, ATP synthetase, is really the powerhouse of the cell, to use a cliche. It gives the primary energy currency for the cell, ATP. It involves oxygen in the first to the second step. And if there's too much oxygen being produced, this can lead to reactive oxygen species. It's an electrochemical step, so you could imagine that happening, a generation of free radicals. If there's too many of these reactive oxygen species, it can cause damage to cellular components, but it also can generate an ROS flux, which sends epigenetic signals to the nucleus, telling the mitochondria there's a lot of oxygen. You should ramp down synthesis of ATP. If this happens because Q10 is artificially depleted, that obviously may have some detrimental effects. I've made another video on taking care of your mitochondria. It's a playful video. It's about a serious subject because if mitochondria in cells are depleted, this can lead to heart disease, cancer, neurological diseases, metabolic diseases, inflammatory responses, even psychiatric disorders, and definitely to aging. And none of us want that. Thank you very much for listening. Bye-bye.